So what will be the work done here? So work done will be equals to how much? Am I audible to you?
Yes, sir.
So work done will be equals to how much? Tell me.
Yes, sir. I'm forming it.
The potential of the edge of a disk is how much? Sigma r by pi epsilon. So in our case, the potential of this disk will be, so this charge is basically dq charge, which you have already put over the perimeter, and then the potential will be sigma r by pi epsilon naught. So this turns out to be sigma r by, and the value of dq we can write as sigma into 2 pi r dr, right?
Yes, sir.
So pi will cancel out. So we left with 2 sigmas. So to find the total work done, we need to integrate this, and this will give us,
Sir, 2 sigma square by epsilon naught only, right?
yeah. I'll just change this. Just a minute. Correct. So pi is already gone, right? So this will be equals to 2 sigma square upon, okay, the pi will not come here again. So 2 sigma square upon epsilon naught into, so the self energy of this turns out to be 2 by 3 sigma square r2 upon, okay. So this is the part which was left. So what else we can do? Okay. So we'll do one more question. I just got the idea. So the idea is, if we have a cylinder, so if we have a cylinder, so let's say we have a hollow cylinder and it is given a uniform charge density everywhere. The length of cylinder we can call is L. The radius we can call it R. Charge given is Q on the lateral surface, curved surface. Okay. So what we do is we take 2 points. Now by symmetricity, we can say that potential of this end must be same as potential of this end. For a given charge distribution, the potential must be same. We have no idea that there is no logic that we should say it's not equal. So because of symmetricity, they must be equal. But if I talk about the potential of the center, it should be different, isn't it? So the question is, can we find the potential difference between the point A and C? Okay, and we can take I think approximation is not required. We can do it like this. So try this question. Find the potential difference between A and C. So which one is? Tell me which one you think is bigger potential, A or C?
Sir, E, sorry, that's C or E, sir?
Yeah, the C should be more, no? Because C
Yes,
is
sir.
nearby the charges. So kind of I'm looking for VC minus VA. That's the question.
Can I just change my laptop? So can I just shift to another place?
Yeah, sure. So I think it's very much calculative, isn't it?
Say, I'm not exactly getting the idea for this.
Okay. So first of all, we need to take for the A part, we have to do it separately. So for A part, we have to take the elementary
So
part.
we like take elementary rings and then calculate it till the
Yeah, till the end.
okay.
So so you cut a ring actually like this. So you move x cut dx. That's like this is like a dx, and we know the potential at the axis of a ring, right? So we can write here as dVA equals to k dq upon x square plus r square under root. That's it, right?
Yes, sir.
So dVA equals to k and dq can write as how much? So q by L dx. That's simple. So this is easy to integrate. So it's kq by L and simply dx by x square plus r square, and the x will go from 0 to L because you have to go for every ring beginning from the A till the right end, right?
Yes, sir. So Q by L is the surface charge.
The q is a total charge, so we are dividing in terms of length. We are just writing q by L lengthwise
So why are we dividing it like only along the lengthwise?
because it will give you the same answer. No? So if you want to write the sigma, it's a round. The charge is everywhere, not on the upper and bottom line. It's everywhere.
Okay, sir.
Charge is over the surface, no?
Yes, sir.
So if you want to know the charge on the dx length, you just need to know the charge per unit length into dx.
Yes, sir.
Okay.
Oh,
Now, how to do this integration? So this integration is a bit difficult, right?
yes, I'm not getting the integration, sir.
Yeah. So I'll just say you. So for integration part, I think we need to use the method of substitution. I can write x equals to r tan theta because then only we can take it out of the root sign, right?
Oh, yes, sir.
R sec square theta d theta. So now this we can write as r sec square theta d theta upon, and this will become r sec theta only, right?
Yes, sir.
So what we get is sec theta d theta, which itself is having the formula ln sec theta plus tan theta. So the answer will be in terms of a ln. So ln, and what is sec theta? So sec theta we can get as 1 plus tan square theta under root plus tan theta. So you may be asking, wondering why I'm writing like this, because tan theta is known to us in terms of x.
Yes, sir.
This becomes 1 plus, sorry, 1 plus x square by r square and x by r. So eventually the answer is ln like this. Okay. So this is the answer. The integration part. I think r, oh sorry, r gets cancelled. No? So we should no r, yeah, that gets cancelled there, but again r will be Yes, okay. Hmm. All right. So this is the answer for the potential formula, right? So now we have to put the limit. So
Yes, sir.
this was a challenging problem actually. And why I'm giving all this problem so that you can learn the integration. Like the difficult part is integration, not the question itself. And also how to take elementary in a different situation. Okay.
Yes, sir.
So the answer comes out to how much? KQ by L multiplied by ln and x square. So we'll just put it like this: x square plus r square plus x whole upon r. Right? This was the answer.
Yes, sir.
Now we have to put the limit also. Limit from 0 to L. Right?
Yes,
The
sir. L by 2. Right, sir.
No, for the A part, it will go from here to no, from everywhere. No?
Oh, yes, sir.
For A, it will go 0 to L. For C, it will go 0 minus L by 2 to plus L by 2.
Oh, yes, sir.
So just let me give you the idea. So V8 turns out to how much? AQ by L. Ln under root of L square plus R square plus L. Minus, if you put 0, you'll get Ln1, which is 0 only. Anyway, this is the answer. So V8 turns out to be KQ by L into Ln under root of L square plus R square. Okay. Now the other
Yes,
part
sir.
is you are not supposed to actually solve the C part. C part is easy because for C part you have to just do the same thing. And because potential is a scalar quantity, the only thing is you change the limit from 0 to L by 2. So let's say for C, I will just integrate from C to the right hand. Okay. And because the left will also contribute equally, so I can just multiply by 2. That's it.
Yes, sir.
Understood what I'm doing here?
Yes, sir.
Okay. So this answer will turns out to be 2Q by L, but in the ln part, it will become R square plus L square by 4. Like this. And now you can take the difference part, the VC minus VA. So I'm leaving this part. Now you can find VC minus VA. Okay, anyway. So if you want, you can take 2 inside out, and it becomes power actually.
Yes, sir.
And now we can take the ratio, so it will become R square. So it's a really bad answer. I'm sorry for that. So we can attach oh, this is the answer. So of course the math was the intention, how to deal with questions in which you have to do the rigorous integration. And integration is simply a skill. Like in physics, if you know how to cut things, how to take elementary, how to manipulate, how to do the integration, it means you are commanding almost 50% of physics, or in fact, I would say 70% of physics. So 70% of physics is pure mathematics, 30% is pure concept and some basic theory. Okay,
Yes, sir.
so there is no end to the question. I can keep on giving a variety of questions. You can keep on solving also. So we'll move towards something called electrostatic pressure.
So can you just come back in a minute?
Yeah, yeah.
sir?
Yeah.
Yes, sir.
So what we mean by the electrostatic pressure? So let's say we have a conductor of some random shape. So this is just some random conductor. So we know that property of conductor says that for any conductor, whether you give some charge or not, the net electric field in the volume of conductor is always zero. So conductor will make sure that any charge given to it is distributed over its surface in such a way that the net field is always zero. So that is a property of charge. I mean, and why it is possible for the conductor to obtain or attain? The answer is the availability of free charge carriers that we call electrons. These free charge carriers, whenever they feel the repulsion, which is unbalanced force, they start moving and they make sure that eventually they come to rest, they attain some equilibrium. And that is only possible when the field is zero. So they keep on moving here and there, and they create their own electric field also, which will eventually cancel the all field. And that is how they balance the zero field within the bulk or volume. So even if you give some charge, it will just spread over the surface. Now, depending on the shape, it may be uniform or non-uniform, which we cannot control how it is going to be. It is the charge which will decide what to do. The way it will, distribute again depends on the shape of the conductor. So let's say this is some random distribution. So we are particularly interested at a particular location. So first of all, you need to realize that the charge is on the few atomic layer of conductor, right? Few atomic layer, like few layers below the physical surface. Understood?
Yes, sir.
So these charges are actually part of the system. So in a way, if you look very close, if you go very close to the surface, what you will see, there is a sheet of charge. Understood?
Yes, sir.
So a very thin layer is going to create a sheet of charge. Like there's a sheet of charge, a thin layer everywhere. Like this, okay? And the charge actually is present here. So it creates the thinnest possible layer of charge. Understood? So this is the reality, and the way we draw for the illustration is not the reality. Of course, I can't put charge on the air, right?
Yes, sir.
If there is charge, it must be in the material medium, because we can't put charge in air or in vacuum. So
Yes,
having we know the property of sheet. So if I cut a small piece of it for the sake of analysis, so if I cut a small piece, I can see a very small thin sheet which is available here. Okay. So just if I zoom out, it may appear to you as a something like this, a thin sheet. Let's call it. Okay. So now, because this is a thin sheet, the property of sheet is that it can create an electric field, right? So imagining this as a disk, we know the near the center of the disk, what is the electric field? If you remember, it is sigma by.
Sir, near the center of the disk.
Yeah. So let's say the sigma of this location. I mean, of course, it's a variable. So let's call the sigma of this location is sigma. So what will be the electric field near the center of a disk above the surface, like not inside, just above, somewhere here, just close to the surface here.
Sir, I don't exactly remember.
You know the formula potential due to this formula?
Yes, sir.
Sorry, field due to this formula. Do you remember?
Yes, sir.
So you can put the x equals to 0, no? So this is like a disk. You're trying to find the field here, no?
Sir, like the electric field only due to the disk.
Yeah, only due to this. Only due to this. What is the formula for the electric field due to disk on its axis?
Sir, I know that in the denominator it will come as x square plus r square to the power 3/2.
You don't
And
remember. You don't remember? No problem.
No, sir.
So the answer was this is radius r, this is x. So the electric field at the point P is sigma upon 2 epsilon naught 1 minus x upon under root of x square plus r. So when x tends to 0, the EP turns out to be how much? So for any disk near the
X
surface,
by r it will become.
no, x tends to 0, so it will become 0 point something 0. No?
Yes, sir.
So the answer will be sigma by 2 epsilon, right?
Oh, yes, sir.
So the whole idea is near the disk, the field is always going to be, I mean, the contribution that the disk can create is sigma by 2 epsilon. So at this location, be very careful what I'm saying. The disk will create an electric field not only up but also down, and this value is going to be sigma by 2 epsilon here and sigma by 2 epsilon here. Now the diagram which I have shown is only representing the contribution due to the disk only, not the conductor, not the conductor. Okay.
Okay,
Now the question is how to get the electric field due to the conductor, which means if you want to find the net value, what is going to be the net value of electric field? So the net value we can only calculate using the Gauss law, because Gauss law only talks about the net value, not the individual value, right?
yes, sir.
So if I create a Gaussian surface, a Gaussian cylinder like this of area dA, okay, area is dA, and sigma of this location is, let's call it sigma only, because I just want to know the answer in terms of some sigma value. So the electric field near the surface is going to be perpendicular only to the surface, correct?
Yes, sir.
The electric field at this location will be perpendicular to the surface, isn't it?
Yes.
So if I call this field as E net, this is the E due to this, or we call it E patch. patch is the small disk which you cut. Now this E is representing the net value. Of course, this is the actual field present there. And the field may be very complex in the field lines may be having complex shape, but near the beginning, near the origin, it is going to be like this one, perpendicular. Okay. So now what is the flux here? If I write the Gauss law, applying Gauss law, so applying Gauss law, what will happen? Tell me.
Uh,
The Gauss law talks
Sir.
about flux, no?
Sir, yes, sir. E into the surface area of the Gaussian surface is equal to the charge by epsilon naught.
Which area will take? The lateral, the flat, which one?
So can we like alter it like according to which surface we are considering?
So the flux will be through which surface? The
The
lateral
flux would
one,
be
flat.
only through. Yes, sir.
Only the flat, no?
Yes, sir.
And that too only on the one side, not on the other side. Because
So is
inside
it because we are considering?
the cylinder,
Yes, sir.
the cylinder is extending just above and just below the surface. The
Yes, sir.
extension of cylinder is just above and just below, but below there is no field, no?
Yes, sir.
See, Gauss law always gives the net field, not individual field. So this is not the field of disk; it's field of the everything, including, right? The entire conductor. What the entire conductor is trying to create near this location. That is what we are trying to calculate using Gauss law. So the net value turns out to be how much?
Sir,
It is clear.
yes, sir.
So the net field is sigma by epsilon naught. That's the idea. Understood?
Yes, sir.
So the question is the E which we got, we can add this E is nothing but E due to patch is E due to remaining.
Yes, sir.
So I'm like dividing the entire contribution into two parts. One, the contribution which is due to the surface just below it, and then B, the contribution due to the remaining surface, and the answer is going to be net value, which is E. So we got E equals to sigma by epsilon naught, and we have seen the value of E patch. So what is E patch?
Right.
So the contribution that will come from the remaining will be how much?
Sigma by 2 epsilon naught.
So it looks like that there is a 50-50 contribution, right?
Yes, sir.
So the idea is the disk will create the field below and up, as you can see here. Okay. But inside the conductor, net field should be 0.
Yes, sir.
So the remaining charge will conspire to make this 0. And to make this 0, the conspiration will be like this. So you will create a net field like this. And the value of field will be sigma by 2 epsilon naught. So the yellow one is the remaining. Understood?
Yes, sir.
And you can see clearly the remaining will add up on the outer side and it will cancel in the inner side. So these two will cancel and so will make the net field 0, and these two will add up to make the field equals to E. Understood? So
Yes, sir.
but what are the takeaways here? So we have to remember, three things. First of all, no matter how you charge the conductor, the net field above the surface of conductor, just above, means not very far, like almost touching, maybe nanometer, micrometer close. So if the point is really close, then the field will be sigma by epsilon naught, which is the net value. But the net value will have two contributor, one, the surface below itself, and the remaining conductor, which you don't realize that they can also contribute. But they do contribute, and we get the contribution in the fashion which can make sure that the value inside the conductor is 0, and the outside conductors, they will add up and will create the net field, which is well supported by the Gauss law, because Gauss law talks about the net field only. So here it is clear that what are the contribution of yours and the remaining. Okay. So now knowing that we have the field value of this much and sigma by epsilon naught for the net and sigma by 2 epsilon naught for the disk below it and the remaining. Now we are in a position to find the force. So let's say I'll just do a small part here. If you consider a patch here, so the patch itself is like a tablet of charge, right?
Yes, sir.
And this charge is, let's call dq, which is equals to sigma into d,
Yes, sir.
and it is kept under which external field? So the field in which it is kept is, tell me, in which field it is kept?
Sir, in the field of E remaining. Sir, I have a doubt, sir.
Yeah.
So in the Gauss law, we are getting sigma by 2 epsilon naught as the E remaining.
No, no.
But
In the Gauss, we are getting this much.
no, sir, due to the like the remaining surface.
After solving, after solving, I get it. Yes.
Sir, but then the remaining surface also produces an equivalent electric field inside the conductor to cancel out that sigma by 2 epsilon naught due to the small patch, right, sir?
Yeah. So you don't create separately, no? Actually, the field due to the patch is up and down, and the field of yours is exactly up. So inside the part, if you look here, it will be having the opposite direction cancel,
Yes, sir.
and outside same direction, so add up.
Yes, sir.
Remaining
when
is
you-
not creating two fields, it's creating only one field. Yes, not you tell me.
Sir, that means technically shouldn't sigma by epsilon not be the external field?
No, how it can be? See, I want to know the force on the patch. So will I consider the field of the patch?
Okay, sir. So that means 1 is sigma by 2 epsilon naught.
Right. I mean, see, who will apply force on me? Myself or somebody else?
Sir, it will be like just the net effect.
Yeah. So the force on a patch, I want to know the force on a patch. So every patch will experience the force due to the remaining electric field, no? Not its own field, isn't it?
Yes.
So the way we write the force on this is the E remaining. So the force on a patch will be equals to charge on the patch into E due to remaining remaining. Okay. So this will be sigma into dA, and this is sigma upon 2 epsilon naught. Okay. So definitely this we can rewrite as sigma square by 2 epsilon naught multiplied by dA. So what is the force per unit area? So the force per unit area is sigma square by,
2 epsilon.
and because this is the force due to the charge body, the charging process. So can we say that this is the pressure experienced by the charge body?
Yes, sir.
So charge is actually kind of embedded in the material the force is on the charge, but because the confinement of charge with the material, the force will transfer to the material part, and hence the material will be under stress. Understood?
Yes, sir.
So what will happen if we keep on putting the charge? Like after some time, first of all, it will be very difficult to put the charge because of the repulsion. And second is, if somehow we are putting the charge, then it is possible the entire conductor may rupture. Okay.
Yes, sir.
So even that is also possible, rupturing of the surface itself.
Yes,
But,
sir.
but that will require a lot of charge. So generally, it happens actually. It's not like it is not happening. So this is how we define the electrostatic pressure. So the electrostatic pressure we can write as sigma square by. So if you know the sigma, you can find the pressure at a given point, and if sigma is uniform, then we can say pressure is also uniform. If sigma is non-uniform, the pressure will be non-uniform. All right.
Yes, sir.
Okay. So we'll try to find the net force on a hemispherical surface charge. So let's say you have some sort of sphere, which is hemisphere. So what? So we have a hemispherical charge, as you can see here. It's a hollow sphere. Okay. And you pour the charge all over the surface uniformly. Maybe we can make it slightly more intuitive in appearance. So it's a hollow sphere. Okay. If you put the charge, then the pressure will be uniform throughout, and it will be pulled by the pressure this way. This is the pressure diagram.
Yes, sir.
If sigma is the surface charge density, so what will be the net force on the sphere? Can you guess? Or you can try for a while, then I'll help. Okay.
Find the net force of the hemisphere, right, sir?
Yeah, yeah. On a hemisphere. My bad.
Sir, are you speaking something? Sir, are you speaking something?
Yeah, I'm saying now. Am I audible to you?
Sir, yes, sir, now you're audible, sir.
Okay, okay. So what I'm saying is, because of symmetricity, we can say the net force is going to be upward, right? The y-axis, along the
Yes, sir.
y-axis. So there are many ways to solve. The one of the ways you can take a ring just like that. If I want you to learn this method actually, and once you take the ring, the force you can always resolve along the y-axis, right?
Yes, sir.
So you can choose a piece of the ring, not even that. You can just take a. Okay, so the force will act in the direction like this system for any given point, isn't it? So this force we can call it dF, which is acting at angle theta, or if you want you can take angle from bottom also, doesn't matter. So this area will be how much? This area. So the way we take the element is like this, if you remember. So I hope you remember. We move theta and we cut d theta, right?
Yes, sir. 2 pi r into r d theta, r being the horizontal radius.
You mean to say this one, right?
Yes, sir.
Very good, excellent. So you remember this one. So now this is theta and this is d theta. So you can find the area of this circular ring which you have cut, and that area we can write as 2 pi small r into r d theta, and small r we can write as r cos theta, right?
Yes, sir.
So we have done this before also in the past many times. So now we can write as the area as 2 pi r square cos theta d theta. So this is the mathematical way. I'll tell you like how to do it without doing all this calculation. So now we got the area. So we can see the force on this area will be how much? Pressure into area is called force. Okay.
Yes, sir.
So what we are looking for is the y component of force, which is df sine theta, isn't it?
Yes, sir.
So if you just think of a force here acting this way, so it's like a ddf, like df I am representing for the entire thing. So first I have taken the elementary, and within that elementary we can take one more elementary, right? Something like this.
Yes, sir.
So if the entire ring will experience the force at df, I can say this as a d of df, but it really doesn't matter. Okay. And the component will be d of df sine theta, the upward, right?
Yes, sir.
So the y component will be d of df. It's very interesting. Sine theta. Okay. But for every element, theta is constant. So every element you will take, theta will be same. So I can take sine theta outside, and this is actually d of df, which gives the df sine theta. So that's why I can write this equation directly. Although it's a angle that, see, the force is everywhere, but technically the force, the y component will be df sine theta. If you don't understand this part, you can leave this. That's okay.
Sir, I understood, sir.
Okay, great. So now what we can do is we got dfy, and we know the formula for df. So dfy we can write as pda, the p electrostatic, basically I can write as p electrostatic into dA into sin theta. So now we have the let me can do. Should I write on next page or here? Right. Just remove this. Not confusing. So now we can say that the dfy is sigma square by 2 epsilon naught, and df we got as 2 pi r square cos theta d theta, right? I think this was the
Yes, sir.
into sin theta. So we are missing sin theta. This was into. Understood. This is fine.
Sir, the electrostatic pressure, like it applies for even like an open surface, sir.
Yeah. The pressure, if it is given to us, let's say, okay, yeah, of course, it's not like this. Think this way: the bottom is, let's say, closed in a way. So this does not apply for the open surface. Actually, it applies for the flow surface. But here, I'm saying that assume this situation, and then try to answer. So let's say this is. That's a really nice question. Can we apply for the open surface? The answer is no. We can apply only when the field in the volume is 0. Okay.
Okay, sir.
Now, if you create a conductor of however thin conductor, it's always a closed surface. So you will have the outer surface, then there's some thickness, then inner surface, isn't it?
Yes, sir.
So there is nothing like an actual open surface. There is always a closed surface. Okay.
Okay, sir.
Any material is always 3-dimensional. Okay. So it is always closed. So that's how we can do this.
So,
Okay.
sir, like inside the inner surface of this hollow hemisphere, also there's charge.
Yeah, it may have a charge. Yeah. So that will create its own pressure on that surface. So we are only bothering about the outer one. The inner one we are not taking into consideration.
Okay, sir.
So the whole idea is just to get the idea of integration and how to find the force. Something we are, of course, ignoring here, because we do have a surface this way, as you have thought correctly, like this. Understood?
Yes, sir.
So the dfy now we can write as 2 will cancel out. Sigma square pi r square upon epsilon naught. I can keep 2 there only, because that will help us.
Sin 2 theta.
Yeah. So into pi r square, then sine 2 theta d theta, which you have to integrate from where to where? The theta will go from 0 to pi by 2.
0 to pi by 2.
And this should be 1 only. I think this is 1. Okay.
Yes, sir.
So, okay, anyway, if you want, you can integrate, but I think this is easy. So we can do it without integration mostly. So in a sine graph, if it is sine x graph, then we know the time period will be 2 pi, but if it is sine 2x, if the time period becomes pi. So this is pi actually, this is pi by 2. Understood?
Yes, sir.
And we are integrating from 0 to pi, so we know that every quadrant is 1 unit. Sine 2 theta. If I shrink it, I think this become 1 only. Yeah, the area will change. So I think this area will be half and half now. Anyway, let's do things. So sine 2 theta is minus cos 2 theta by 2. Okay.
Yes, sir.
So this is exactly how much? Minus cos pi by 2 means into is that's cos pi actually. And plus cos 0. The answer is 1. Yeah, the 1 is the right answer. Okay. So now if you shrink the graph, I think this becomes half and half. For the full graph, it was 1 and 1. Area by, so anyway, this will become sigma square by epsilon naught 1 by 2 like this into pi r square. So this is a really lengthy method to do this, but the whole purpose was not this method, basically to demonstrate how to do the integration in calculating the force when the things are radial or pressure is radial. So that will be very helpful in solving even other questions. So generally we can do this almost in one line. I mean, not doing all of these. So let's say we have again a hemisphere. And so what we do is we take a small patch. Just think of a small patch somewhere. And if you think of this as a patch, a small patch, then the field will be so the force will be how much? Sigma dA into electric field,
Yes, sir.
which is sigma square by sigma by 2 epsilon, right?
Sigma by 2. Yes, sir.
Simply force into field QE. QE is the answer. So our answer is basically dA. And what we're looking for is we're looking for the y component. So if I take as theta, so the y component of course will be how much? Cos theta. So you can say dfy is simply df cos theta. Okay.
Yes, sir.
And if you look carefully, this is sigma square by 2 epsilon naught into dA cos theta. So the dfy we got is sigma square by 2 epsilon naught.
So this is basically without considering elementary ring and just
Yeah,
considering
yeah.
an elementary patch. So
Correct. So now we have to just integrate this, right? So the
yes,
net force is sigma square by 2 epsilon naught. But this is interesting. What is dA cos theta? So this is like you're turning this patch horizontally, no? So the dA cos theta is basically you will realize that it is a projection on the base actually. It's the shadow of the patch at the base. Understood? This is the shadow of the patch here.
Oh, right,
Shadow.
the component.
Yeah, component, or you can say shadow.
Yes, sir.
So this is the dA cos theta is called shadow or the patch. If I take the shadow of every patch, it must cover the entire base,
Yes, sir.
isn't it?
Yes, sir.
And therefore, this is nothing but the area of the base. So this is nothing but the projected area, which is equals to area of the base. Understood?
Yes, sir.
And therefore, the force turns out to be sigma square by 2 epsilon naught into pi r square. Now it is easy.
Yes, sir.
So I think this is same as before, right? Same answer.
Yes, sir. Sir, I still don't understand how we apply the electrostatic pressure formula that we derived, sir. Like
So
you told,
the pressure is always perpendicular to the surface. So if you know the surface,
sir, no, sir, like for, you told like it's applied only for closed surface, but then we are considering this to be pretty much like an open surface. And
no, okay. For conductor, every conductor if you create is always a closed surface.
yes, sir, but
And
it's a closed surface if
so
we
we are,
consider it
yeah,
inner
yeah. So
hemisphere.
we are finding the force only on the outer part. If I consider the inner charge also, then the force will become zero.
Oh,
It means if you consider the patch, the pressure on the outer, there is a thickness of the patch, not patch, thickness of the shell.
yes, sir.
So the upper surface will experience the pressure outward, but the lower will experience the pressure inward.
Yes, sir.
So the net force is zero.
Okay. Yes,
But
sir.
we are as of now we are simply considering the charge on the outer surface. Inner we are ignoring. I mean, just we are doing the calculation, not the reality. I'll come to that. Why we are able to solve this just in a while. Okay.
Oh, yes, sir.
So I know what is your confusion, but that's okay. I mean, you should have the confusion. So this is the electrostatic pressure is not just about conductor. It is about anything in which the inner field is zero. So let's say I consider something like a non-conducting shell. So if it is a non-conducting spherical shell, if you give charge to the shell, it will be like this one. Now, what is the electric field inside the shell? Tell me.
Sir, it's zero.
And what is the net field just outside the surface?
Sir,
KQ by R square. The
yes,
formula of electric field, KQ by R square, no? It's like point charge.
yes, sir.
Even if you don't know,
Like all the charges are concentrated at a point. That's how the spherical shell behaves.
yeah. So let's say if you want to write in terms of sigma, so E on the surface, I mean just outside, is KQ by R square, but you can look this as a Q by 4 pi epsilon naught R square, but you can also look as Q by 4 pi R square into epsilon, which you can write as sigma by epsilon exactly, isn't it?
Yes, sir.
So if you apply the Gauss law over the surface, because the inside there is no field, the net field will be always sigma by epsilon naught. That's the rule. I mean, you can always derive like this. So any surface in which the enclosed volume do not have electric field, the field just outside the surface will be sigma by how much? 2 epsilon naught.
Epsilon. Yes, sir.
Understood? Okay. All right. So if I want to know the field due to the patch only, this patch. So what is the contribution of this patch? So if you go really close to the patch, you know the patch will create the field this way and this way both.
Yes, sir.
And because you are very close to the patch, we can consider this as infinite disk.
Yes, sir.
And due to infinite disk, near its center is always this value.
Yes, sir.
So the remaining will try to cancel the inner field because we know from Gauss law the net field is inside 0.
Yes, sir.
So the yellow arrow is representing the field due to the remaining charge, except the patch, which is also sigma by 2 epsilon naught, and therefore outside it will add up, inside it is again 0. Understood?
Yes, sir.
So again, this shell will also experience the electrostatic pressure by the same formula. Understood?
Yes, sir.
And this is not a conductor. This is not a conductor.
So it can apply to anything that has net electric field of 0 inside.
Yeah. So
Yes, sir.
let's say if I create a conducting shell, maybe you can think like a thick ball, something like this. Let's say you have a so you can realize something here. What is happening? So this is not a hollow, it's a thick shell. I'm just drawing it. Okay. It's a thick shell. So if I try to give a charge here, the charge will spread here. This is a thin shell, but I have just zoomed. The charge will be on the surface here because you can see it's a big one looking like. And then the charge will also appear in the inner one. The charge is everywhere, understood?
Yes, sir.
And the electrostatic pressure will be normal to the surface anywhere. Here like this, here like this, here like this. It's this way actually. Understood?
Yes, sir.
So what I did was I said, okay, ignore the inner one. Just think of the outer one charge. Then can you calculate the field? So if you just consider this particular thickness, you can get the same sort of answer. No? The inner is 0.
Yes, sir.
The outer will be sigma by absolute net value. And the
Yes, sir.
patch will have the half of this value contribution, remaining will have the half. Again, same trick.
Yes, sir.
So that is the idea of finding doing the calculation. So it is also closed surface. No?
Yes, sir.
Even if I make it a hypothetically very thin shell, can you make it a 0 thickness shell?
No, sir.
So the surface will be like almost overlapping surface. It doesn't look like two surfaces, it looks like one surface, but we have two surfaces, and so it's a closed volume, isn't it?
Yes, sir.
Just okay. Anyway, so this part is done. So there's a very famous question called soap bubble, and when you put some charge on the bubble, the pressure will be pulling the bubble, isn't it?
Yes,
So
sir.
think this as a soap bubble. So if it is a soap bubble, then the pressure will pull it outward, isn't it? So charging of soap bubble will create a outward pull. The question is, the pull will depend on, so the direction of pressure will depend on charge or remain same. So what if I may bring a negative charge? The answer will change or remain same.
Sir, it will remain same.
Correct. Because when the charge will be negative, field will reverse and the force will again reverse. So it will remain
Yes,
same.
sir. Yes,
So
sir.
field will be inward, but on a negative charge, force is opposite of the field, so force will remain still outward. So no matter whether you put positive charge or negative charge, the pressure always acts readily outward, or you can say normal to the surface, and therefore, upon charging a bubble, it generally expands. For the obvious reason, the pressure will pull. Understood?
Yes, sir.
So charging process expand the soap bubble. I hope this is clear.
Yes, sir.
So the question was, there was a question in JE Advanced. I think maybe mains or advanced. So imagine we have a shell like this, but it is not a single shell, rather it's a two half piece joined together. Okay. So it is like someone is holding them together by pressing like this. So now this will look like a shell. Okay. And what do they do next is they put the charge over the shell. So if you put a charge, let's say sigma is the surface charge density everywhere on both sides. So it looks like a shell, but we can understand it's not a shell. Okay. So
Yes,
these are
sir.
like two half pieces joined together. So if I think two pieces as two positive charge bodies, so they will repel each other.
Yes, sir.
So keeping them in this uh, orientation or this configuration, it needs some external effort, right?
Yes, sir.
So the question is, what is the minimum force required to keep them together? Find F minimum to keep them together.
So,
Yeah.
sir, it is actually the electrostatic pressure that's keep like trying to pull them apart,
Yeah,
right,
yeah.
sir?
You can think that is actually the reality. See, it's very interesting question. See, if I just think of the half part, and if you give some charge, the charge will be like spread everywhere like this, not only here.
Yes, sir.
The same thing is true for the other half. But as you brought them closer, what will happen? The charge will start coming out. I mean, it will leave the part.
Yes, sir.
They will start flowing. At the moment you are almost about to close, all charge will leave it. So
Yes, sir.
the sigma at that instant will be on the outer surface only, and then of course they will exert the electrostatic pressure. So the force will be trying to balance the. See, you can draw the ABD of only one single one. So you can draw the ABD of single part, only one half.
Yes, sir. And the net force on it will be due to the electrostatic pressure.
Yeah. So if you just draw the one part, if I just remove this. So if I draw only one part, the thing which will happen here is you are applying for this way.
Yes, sir.
The other force is due to the electrostatic pressure, na?
Yes, sir.
And we know the answer. So the F must be balancing this one, right?
Yes, sir.
So F will be equals to sigma square by 2 of naught into pi r square, the base area, right? If you remember the answer.
Yes, sir.
So this is the simple answer. This was a JE question, and yeah, you can get the answer easily. All right. So if they give charge value, you can substitute the charge in terms of sigma to get the answer.
Yes, sir.
So, I think we are done with this also. Anything left? Okay.
So dipole moment due to.
Yeah, that is there. That is there. No, before that, I mean, I just want to know if some question I should give it to you now. Just so there's one more concept that's called the so we have done this briefly in the earlier chapter, but we'll do it once again. So let's say if we have a conducting sheet, so you can think that sheet is like this actually. I'm drawing like this. Okay. And we have a charge here. So if it is a metallic sheet, then what happens that the electric lines of force cannot penetrate this sheet, so it will just terminate on the sheet. And to do so, we know that it has to induce some negative charge, right? Some negative charge.
Yes, sir.
And similarly, it will create a field like this. And they will. This
Sir,
will,
I think we discussed about this method, sir.
yeah, yeah. So we'll just try to extend this method a little bit beyond actually. So now, if you make this conductor grounded, the potential of this conductor will be zero, right?
Yes, sir.
So now, because potential is 0, so we can create a hypothetical situation in which the charge is there, and exactly at a twice of the distance from the conductor. So if I call this distance as d, it will have a mirror image. The conductor will act as a mirror image, and we will have a charge here, and the mirror charge will be having opposite polarity.
Yes, sir.
And if this is q, this is also q. And why this assumption is valid? Because if you just consider a opposite negative charge, then the potential at any point will have equal contribution from the up and below, and this will add up to 0. Understood? So no matter where you go on this line, this line will behave as a 0 potential plane. This, or not line, this is the plane actually. So the plane will behave as a 0 potential plane, and by assuming equal charge on up, top and bottom, we are actually making this possible. So we are recreating the situation, and therefore this is the equivalent diagram. So you can replace this by a single plus minus, and then you can find the force between them also. So force will be how much? AQ square by 4d square. Now, if I try to move a charge a bit, so let's say the next question is, so we have a conducting sphere. So we have a conducting plane again, and this is the charge, and this charge is at a distance of d. Let's say d. Let's say you want to move this charge by a value x. How much work is required to move by x? Find work done in moving charge away from the sheet by distance x. Okay. So you have to think this way. So initially we have to think as a charge is q here and charge is minus q here at a distance 2d. But once you move it, it will be like this. And now this will be twice of d plus x.
Yes, sir.
So the potential energy in the initial situation is how much? You can find the potential energy formula minus kq square by 2d.
Yes, sir.
But the potential energy finally will be how much? Minus kq square by 2d plus x.
Yes, sir.
So change in potential energy is how much?
So UF minus UI. Sir, can you just take my charger and come, sir?
Yeah, sure.
sir.
Yeah.
Yes, sir.
Okay. So the question is, we can find the delta U, and the delta U turns out to be minus k. Okay, I can just write because it's minus sign, so we can write as kq square by 2 1 by d minus 1 by d plus x, right?
Yes, sir.
And this turns out to be x upon d into d plus x, right?
Yes, sir.
But this is a change in potential energy. So the question is, what is the work done by the applied force? And the answer will not be delta U. Answer will be half of this value. Why? So, okay, let me do this question in other way around. So, if I apply the force to move this, so let's say so we got delta U, but we have to just wait for some time. If we have the same conducting sheet, which is grounded, and we have a charge at a distance d, and we know the force. If I say the in the general separation, if I call it R, how much force it will experience? Kq square by 4r square in general, right? At a distance R. So dw will be how much? F external dr, isn't it? Am I audible to you?
Yes, sir.
So we got the delta U. Now we are trying to find the work done actually by the force applied. So if you're applying a force F, and if at any instant the separation is R, the other charge will appear at minus R, as like R below.
Yes, sir.
So force at any instant will be this much. So work will be how much? If you try to pull it slightly up, the work will be how much? This one.
Yes, sir.
So the work done by external will be kq square by 4 into dr by r square from d to d plus x, isn't it?
Yes, sir.
So this turns out to be kq square by 4 and 1 by d minus 1 by d plus x, and you can see it's a half of this value. And if you look at this answer, the answer which we got, the delta U, it's a kq square 2. So why the work will be half of this value? That's the question. Why we cannot just equate it? Because here the half, the part which we consider, which is the mirror image. So in reality, we have to understand two things. So if you try to draw the lines of force, the lines of force will start from here and will terminate here. But
Yes, sir.
when we calculate the energy, we are considering this as two charge without the boundary, isn't it?
Yes, sir.
So half of the energy is actually not part of our calculation. So you can say the field lines that we consider is only half of it, not the full lines, right?
Yes, sir.
So the energy is actually spread on the two sides of this boundary by equal values. So the delta U which you get, is actually delta U on both sides. Okay.
Yes,
So
sir.
each side will only contribute half of the value. And this is the fictitious reason, right? So the bottom is the fictitious reason. It's not actually present, isn't it? So when you try to calculate the delta U, you get the energy of the entire system, assuming there is no boundary and field is everywhere. So if you cut half the field, the energy will also cut by half value,
Yes, sir.
because the field is nothing but the sorry, energy is nothing but the field only. So if I cut the extent of field by half, actually what I'll get is the half energy. So in the calculation by the energy method, we generally get a wrong answer. The reason is we take the other virtual half which is not actually present. Understood?
Yes, sir.
So this is slightly difficult. So the doing the actual calculation is easier. This is easier for you because this is you're actually trying to calculate the work done by the force. And energy method is giving the answer, but with a condition that you have to be careful that energy is actually available on only one side. So there is no energy this side. So the energy on this side is how much?
Half of
Energy,
the act. Yes, sir.
energy on this side is 0. So all of it, see the energy that we have calculated is assuming that energy is equally present on both sides. So in our calculation, we are considering the energy is present equally on both sides of the boundary. If I cut the inverse into two halves, and if I assume the energy is on the entire inverse, so one half of the inverse will be only one half of the energy, isn't it?
Yes, sir.
And because the plane is terminating the field line, so we are getting only half of the energy. That is why the work done that you actually do is only half. The other half appears automatically. So you can think that way. That's why this is a difficult one. Understood?
Yes, sir.
Okay. So now this is not only restricted to the plane. I mean, this is like a mirror. So always you can create a mirror concept. So when you study the ray optics or the geometrical optics, so let's say if we have a situation in which we have two conductors which are mutually perpendicular like this. So we have two conductors which are mutually perpendicular, and now this is also infinity. This is also infinity, and what you do is you put a charge here somewhere, and let's say let's say this is origin says x-axis, and this is y-axis. I'm calling the coordinate of this charge particle as a comma a. So if the coordinate of this charge particle is a comma a, then from the concept of optics, you will come to know that both will act as a mirror. So this mirror, the vertical mirror will form the image here, where?
Minus a comma.
Correct.
A.
So I'll just get a thin line.
So 3 images will be formed.
Yeah, actually 3 will form. So all images will be on the on a circle actually, and the intersection of the conductor will act as a radius, or sorry, the center. So basically, here we will have a circle. Like this, right? All images formed on a circle. Okay. So the first image will be from the vertical. So the vertical mirror will form the image of this charge here, and because it's opposite in polarity, so it will form negative. This charge will be from this. So the other image will be from this minus Q here.
Yes, sir.
Now the both mirror, they have done their job. So we have now 2 images. Now this will come to this one. This is done. Come here. This will form. So this is behind the vertical mirror. This charge is behind the vertical mirror, isn't it?
Yes, sir.
So if the object is behind the mirror cannot form the image, isn't it? So we can form the image only when the object is in front of mirror.
Yes, sir.
So this object is in front of or in back of mirror.
So it's behind the mirror.
It's behind the vertical mirror,
Yes, sir.
but it is in front of the horizontal mirror, isn't it? If you
Yes, sir.
extend this line, you can see, and therefore the other,
Yes, sir.
so the bottom mirror will form the image of this charge here. Plus, okay.
Yes, sir.
Similarly, okay, this is done. What about this one? This is
So
behind the
that will
horizontal.
form.
Yeah, this is behind the bottom, but in front of the, vertical.
Yes, sir.
So this will form the image which will coincide with the already existing image.
So both will coincide. Yes,
Yeah,
sir.
we will not double it. We'll just keep it one image. And then now we have only this charge, the last charge. This charge is behind both the mirrors. So nothing will happen. This charge is behind both the mirrors, isn't it?
Yes, sir.
So none of the mirror can form its image further. So this is the end of the image formation. We will have 3 images. Okay. Clear?
Yes, sir.
So once you know the charge distribution due to the plane mirror, you can remove the mirror, and then I may ask you the question. I may ask you the question that if this is A, if I make it a two-way, what will be the work done? So if if charge Q is taken from AA to two-way, then what will be the work done by external? So what will be the minimum work done, because I'm doing externally, minimum work done by external agent to do so? So you need to find the mutual potential energy of the system. So you will
Yes,
find the
sir.
final and initial, but the work will be how much? By 2 or by 4 or by 1? So this is like a octant, no? Sorry, quadrant. You can think this quadrant. So this is like a quadrant, and because this is like a quadrant, so what you can say? The energy will be
Sir,
part
the
of 4
energy of four system, I mean, like it's as if like there are 4 particles in the system, but in actuality it's one. So
Yeah, no. What I'm saying is, it is like the whatever you find the delta U for the beginning and the end case, the energy will be divided into 4 equal parts. So the inverse is now divided into 4 parts. No?
yes, sir.
So the lines of force is actually present in which region? Only in the first quadrant. No?
Yes, sir.
We don't have lines of force in the other region, isn't it?
Yes, sir.
So this will be by 4 now. That's the only trick. So earlier the plane was divided into 2 parts. Correct? So a plane which is infinite plane will divide the inverse into 2 parts. No? This is infinite in all sense. So the work done will be, because we have energy in this quadrant and this quadrant, and our world is in the upper quadrant, right? The upper 2 quadrants. You can see.
Yes, sir.
So this kind of logic we have to develop, that what is the work done by the external? The answer is delta U by 4. Is this clear?
Yes, sir.
Therefore, you need to first find the UI. So what is UI, by the way? We know how to do this initial and final. So the potential energy, this is a 4 charge particle. We know how to find the potential energy of system of 4 particles on a square. So it's the alternate charge, na? Plus minus, it's alternate charge. We can do it easily. Do it for anyone. Let's do it for this one. K on the right, it will be Q minus Q by 2A plus KQ into Q by root 2A. And then this term will be twice from above. And this whole term will multiply by 4 and by 2. That's simple answer, right? I
Yes,
hope
sir.
you remember the mutual potential energy calculation.
Yes,
So
sir.
it turns out to be KQ square by 2A we can take common. And therefore, what will left will be like 1 by root 2 minus 2. Or it's a negative answer, definitely. So the UI is minus KQ square by 2A, 2 minus 1 by root 2, because that's negative. So the final we need not to calculate, we can just substitute the A by 2A, right?
Yes, sir.
And therefore, the delta will be how much?
Minus KQ square by 4A into 2 minus 1 by root 2.
So it will become plus, no? KQ square
Oh,
of 4.
yes, sir.
And therefore, the work done will be 1/4 of that value. So it's a KQ square by 16A 2 minus 1. I hope this is okay, clear.
Yes, sir.
So one last question to end this discussion. And the other question they may ask you that can you find the force? So we can find the force on any charge particle, net force.
Yes, sir.
So one will repel and other will attract. So the diagonal will repel and these two will attract. So the attraction seems to be more actually, but maybe less. So net force will be F1, F1, F2. So we can write as F net equals to, I'm writing here only, F2 minus root 2 F1. Like downward.
Yes, sir.
And F2 we can write as KQ square by like root 2 2A whole square, which is 8A square. Sorry, 8A square minus root 2 F1 is how much? Value wise, because we have taken a direction KQ square by 4A square. That's it.
Yes, sir.
So of course this is bigger one, so you can just change the minus sign. So this is the net force value, and we can do
So,
the answer easily. Yes, sir.
sir, the work, sir, like the potential energy dividing it by 4, can you explain it by like field lines?
Yeah, the field lines here is slightly difficult to draw. Okay, so I'll just show you. Just show. So can you see the new screen?
Sir, yes, sir.
So let's say I put a plus charge. This is the field lines of plus charge, roughly.
Yes, sir.
Now, if I bring a negative charge in front of this, you can see this is the new field.
Yes, sir.
Now, these are computer simulations, so it cannot be exact, just for an idea. And then plus charges I'm bringing here again. You can see the field lines are like this. And then
Yes.
a minus charge here to emulate our discussion. So if I annotate, you can see something. Let me annotate. So you can see the field lines here is like this, but it is going somewhere here. It is going something like this, something like this. And it is going this way.
So like only 1/4 of it of the interactions
Yeah.
is
But
actually present.
yeah, the whole idea is we have a symmetrical distribution everywhere. If I cut into 4 quadrants, the field lines are similar in all 4 quadrants, isn't it?
Yes, sir.
So when I calculate the energy belongs to the entire universe. So
Yes, sir.
I am only taking this energy, na? So that's why 1/4. Understood?
Yes, sir.
So basically, the work done is actually equals to the U final by 4 minus U initial by 4. Or you can just do the difference and take divided by 4. So that's up to you. Understood?
Yes, sir.
So this is the FIT Colorado. I have given this site name in the very beginning when I was teaching chapter like a vector. You can do the simulation and you can actually practice whatever you want. So this is a really nice website, free of cost, nothing you need to pay.
Yes, sir.
So in the entire America, they use this free software or free open resource to teach. And nowadays, most of the experimental teachings are done on this site, even in the regular American school actually. So I hope that even in your school, if it is international board, they use this. Yours is CBSE, right?
Yes, sir.
Yeah. So anyway, this was the whole idea. You can go back. Okay. So this part is clear.
Yes, sir.
So in fact, we can do something more interesting here. Let's say if I have 2 conductors, which is creating 60 degrees. So if 2 conductors are at 60-degree inclination, and if charge is kept here somewhere here, then now you will get how many images? So if it's 60 degrees, so the number of images will be 360 by the angle, which will give you 6, which is like a even number. So you will study later on. So the number of images will be 5, because 1 object and 5 images. In total 6. Okay. So because we have 6 images, so this will turn out to be, you know what? Like a hexagon. So I need to do a bigger line, but ideally should be only hexagon. I think the 60 degrees is very small. Let me make it bigger. Oh. I'll do the reverse process. This diagram is difficult to draw. So first you draw the circle, then you draw a hexagon. So the hexagon we can draw like Hopefully this should be the right shape. So I cannot draw the exact diagram, but you can understand this. And the conductors are like this. Actually, this is the conductor. Not like this. Yeah, somewhat like this. And the charge is here. I mean, let me do this charge. So the first image will be here, minus q minus q. Then the next image will be plus q plus q. And the last will be exactly here, which is again minus. Understood? Maybe somewhat.
Yes, sir.
So now this actually they have given single charge, but these are conductors. And therefore, a single charge will convert into a hexagonal distribution, and we know how to find the mutual potential energy, right?
Yes, sir.
So now the if I change the, I mean again the same question, like if I change the distance, so let's say the distance from here is r. So if I make it 2r, then what will happen? It will go on a bigger circle, right?
Yes, sir.
And because it's a hexagon, so the r will become the side length this also. So r will also become the side length because it's the equilateral triangle, right?
Yes, sir. So without the structure getting altered, it will become a bigger circle.
Yeah. The shape will remain same, on dimension will change, right?
Yes, sir.
So if I take the distance from r to 2r, then in that case the work done by the external will be delta u upon.
6.
Now you know why it is 6, because the inverse is now symmetrically distributed into 6
6.
equal part, you can say. So energy of each part is just 1/6, right?
Yes, sir.
So questions like image charges comes in Olympiad examination, or maybe sometime later JE may try this concept also, and therefore we can get the answer.
Okay, sir.
One more concept which is very very important, which I don't know how I forgot. This is called potential due to induced charge. Potential due to induced charge. So let's say we have a spherical conductor. So we have and from the center of this spherical conductor, we have a charge. And the distance is d. And the radius of this conductor is Let's call it R. So D is not very far. So if you bring a charge nearby the conductor, it will create the induction, right? So some positive, some negative charge will appear here.
Yes, sir.
Some negative charge will appear here, and on the other side, some positive will appear this side. Isn't it?
Yes, sir.
So we have a negative and positive charge. This is called induced charge. This is the induced charge. Okay. Now, because of the spherical symmetricity, if you look carefully at the center of the sphere, the potential at O will be potential due to Q plus potential due to induced charge. Isn't it?
Yes, sir.
So the Q will create how much potential? KQ by D.
Yes, sir.
So what about the potential of the induced charge? Because the center is equidistant from all the plus and minus
Sir,
charge.
K and sir, the induced charge would be equal to that of Q, right, sir?
Yeah, so minus Q and plus.
So minus Q and plus Q, would they cancel out then?
So the zero answer.
Yes, sir.
So the induced charge will have zero contribution at the center of sphere. Understood?
Yes, sir.
The total potential which we get at the center is just KQ by D. But the concept which we know about conductor, that in a conductor, the net field is zero. So potential difference between any 2 points will be zero.
Yes, sir.
So the potential at O, although you got the answer at O, but the potential of the entire volume is going to be constant only, no?
Yes, sir.
So although the answer was easy for the O point, that's why we did this, but the answer will be true for every other point as well. So the answer, the net potential at any point of conductor is always V. So potential at any point so I can write in words. So since conductor volume act as equipotential volume, therefore potential at every point of volume will be equals to V naught. Okay, it is clear.
Yes, sir.
So let's say if I ask you what is the potential at this point, so let's say the answer is potential at this point. The answer is
So just inside the surface?
just inside surface. So
So
potential,
there also it will be same.
yeah. So potential at point P again will be potential at point P due to Q plus potential at point P due to induced charge. Right?
Yes, sir.
Potential at point P will be equals to KQ by D. Potential at point P due to the given charge will be how much? KQ by D plus R. Understood?
Yes, sir.
So potential contribution due to the induced charge will be how much? You can get the answer. So the induced charge will actually contribute 1 by D minus 1 by D plus R. Understood? Which is K
Okay, sir.
cube R upon D into D plus R. I hope this is clear.
Yes, sir.
So induced charge will contribute differently and so the given charge, but the sum will be same, that is the take up.
Yes, sir.
I hope this is clear.
Yes, sir.
So now this is where we can end our journey of the electrostatics. The next part will be dipole moment. Okay. And
Okay.
just let me just check if something is still I need to take care. So I hope you have all the PDF together no, of electrostatics.
Yes, sir.
Yeah. So you know how to merge PDF together? No,
No, sir.
don't worry. Okay. So when we'll end this chapter, you will just share the PDF. I will merge and I'll convert it to a book. Again, I will send you. So you will have the all PDF at once.
Okay, sir.
Because electrostatics is very, very important, right?
Yes, sir.
Okay. So I think we have done most part of it. So nothing much is needed. Okay.
Sir,
Yeah.
sir, after the class, can you forward the
Yeah.
videos recordings?
Yeah. Sure. Sure. I'll do it. I just forgot that day, but I'll do it today.
Okay, sir.
Not in fact what I mean, I was taking lecture nowadays. I'm taking lecture till 12 a.m. in the morning. So after that, I just go to sleep actually. So that's why I'm forgetting. Anyway, so this is another session. Okay, fine. Yeah, so most of it we have done. So now we are good to go with the dipole part. So we'll start in the next lecture. Okay.
Okay, sir.
So tomorrow is Saturday. Tomorrow I won't keep any lecture. All right.
Yes, sir.
So maybe on Sunday evening I'll keep. I mean, if possible, but hopefully, I mean, we can start from Monday. Okay.
Okay, sir. Sir, but then Sunday evening, Akash sir's class is also there, sir.
Yeah. So then Monday on. Okay.
Okay, sir. Thank you, sir.
Okay, bye. Take
Bye,
care.
sir.